Hello, everyone. So I'm Jonas Ries from the EMBL in Heidelberg. It's really a huge pleasure for me to chair this first part of the DECODE workshop. So DECODE is the result of, I think, really fantastic collaboration among 3 groups scattered worldwide. And we started kind of separately and found each other then. And then each of us contributed basically what we know best to come up with what I think quite a useful product. And this is what we want to share with you today. So let me start by briefly introducing the two today. Let's start with Lucas, who will give the presentation in the beginning from my group. He did his master's project in my group and then now moved on. Artur, who is all over the world. Now he is, I think, back in Munich. Then Srini from Janilia. And the person who is missing here, or the two people, are Jakob Macke from Tübingen, and Anna Kraszuk from the EMBL also contributed a bit. So what we thought would be quite nice, if each of you can also introduce yourself briefly in the Slack channel. And I think all of you found the DECODE for single molecule localization microscopy Slack channel. Would be nice if you all locate it and then write a sentence or two about yourself. And Ulrike, I forgot. Sorry, Ulrike. She is joining us in the session and supporting us also in Janilia. So I think with this, let's start. And and Lucas, the screen is yours.
Yes. Okay. You can see and hear me, right? Then let's start. Also, a warm welcome from my side to this workshop today, the DECODE workshop. Deep learning enables fast and dense single molecule localization with high accuracy. As Jonas already kindly introduced, the collaboration of a few institutes and a couple of people. So before we dive right in, Jonas mentioned it already. It would be cool if you sign up and join the respective channel of the conference, so that we can post links there if there's something is to do there, or some more information or help you out. And also you can visit us at the DECODE hut in Gather. Okay. The workshop's program is basically split in 4 parts. So we will have a research talk now in the beginning, an introduction to DECODE. We will then present to you the online workflow, have a bit more of an extended socializing and break after that, and we'll then continue with the local workflow on your own respective machines. Each of those question and answers is followed by a short break, which I have not mentioned here. Good. What is DECODE about? DECODE is a deep learning-based fitting algorithm for single molecule localization microscopy. It is specifically designed for accurate high density and 3D localization. And as it is for high density data, it enables high speed, ultra high labeling, and also lifestyle single molecule localization. The two main components, or most interesting components, are that it uses temporal context and that we provide a meaningful uncertainty measure. Both of those things I will talk about later on, and then really introduce them to you. So most of you probably know, but just a short recap. What is localization microscopy about? It is about going, let me get my pointer here. It is about going here from the diffraction limited image on the left to a super resolved image on the right. As you all know, there's the diffraction limit in microscopy, and basically localization microscopy is about the trick to split the signal over thousands of frames and then to fit these emitters. So how does it look like? If you have your frame stack here, I'm sorry, but maybe then we continue here. So if this is one of the frames in your frame stack, what you typically would do in your localization procedure, you would extract maybe a ROI around the emitter and fit a couple of parameters to these emitters. Typically, this would be the position in XYZ, and the brightness, or maybe even additional attributes of these emitters. And then if you do this for all the frames and all the emitters on the respective frames, you would end up with a list of localization and a nicely resolved and rendered microscopy image. But what is now the problem, of course, of a localization microscopy? It is by design a bit slow, because like the idea was that you split it in multiple frames, right? So you kind of need the time for the acquisition. So here on the left, I've put an example of like a rather low density case with 150K frames, which could correspond to a 2-hour acquisition. But then you can imagine the number of emitters directly correlates to the acquisition time. That is, if you increase the density on a single frame, you need less frames and therefore decrease the acquisition time. So if you now then go to these what we call high density cases, we clearly see that we leave the single molecule regime, right? Because the distance between the emitters in this high density setting is comparable to the extent of the PSF, right? So you clearly see that it's quite crowded here. And at the bottom, I've depicted a state-of-the-art reconstruction of this high density data shown here. But of course, you also know that if you only need 10,000 frames, then your acquisition time is quite like reduced by quite a bit. But what is now the knowledge gap? What is missing in the field? In general, we have many fitting algorithms for localization microscopy. To name only 3, Thunderstorm is quite a prominent, C-spline and SMAP maybe, and those classical fitting algorithm like typically use a 2-step procedure. So in the first step, they would extract like quite coarsely where they have some kind of signal. So they would extract the ROI and have some kind of like initial guess of the position of an emitter depicted in green here. And then in a second subsequent step, they would fit within this ROI to their PSF model function. And this is also interesting, or the thing which is interesting here is also that for 3D high density cases, the best algorithms in the localization microscopy challenge were in fact oft algorithms which were designed for low density. Right, so you can see here that there's some missing edge. And here in the middle, you see one of those cases of high density where you have maybe 2 detections, but then your fitting procedure, your optimization converges to a suboptimal local minimum, and you will lose this detection basically. So now in DECODE, we do it a bit differently. We don't have this explicit 2-step procedure of detection and localization, but we rather do it jointly and then don't have this problem in the high density cases. The fitting procedure overall looks like this. We have an image sequence in the beginning. We feed this through our DECODE network, have then a couple of different representations of these predictions, extract the localizations, and then end up with the rendering. So I will now show you this in a bit more detail, how it looks like. Okay, so if you think about the characteristics of an emitter, you will probably know that like an emitter activation is a stochastic thing. So usually you say that an emitter appears at some point in time, for example here, right? And then has a certain lifetime, which follows an exponential distribution mostly. And the interesting thing is that in a classical, or for most classical fitters, what you would do is you would just fit each frame at a time. So you would just go through them sequentially and fit the individual ones, and maybe have some post-processing, some grouping procedure, but the fitting itself is in most of the cases done only on a single frame. But we now thought, okay, if we have this dynamics of the fitters, which are apparent in multiple frames, why don't we let our model enjoy this help of the emitter's characteristics? So what we did was, instead of inputting a single frame at a time, we input a window of 3 frames, right? So we always want to fit the emitters, which are apparent on the middle frame, on the target frame. But you can see here in this figure that quite many of these emitters which are visible here are also on the what we call auxiliary frames, right? You see that some of them are maybe a bit more dim on the auxiliary frames. Some of them are not at all on the auxiliary frames. And of course, some are only on the auxiliary frames. But a great share of those on the target frame are also on the auxiliary frames. Here on the left and on the right. We then measured in an ablation study whether this is beneficial or not. So what we did was we trained our model in the very same manner. The only difference was that in the one model, we only had a single frame, and in the other model, we had this frame window of 3 frames. And here on the right, I have the figure of our manuscript. So basically, we measured the detection accuracy, the Chakar index, and the localization error over a different density regime, right? So here on the left, you see it's quite sparse. So this is clearly single emitter, and here on the right, it's quite dense, right? What we also did, we measured this for 3 signal to noise ratios, and then the dashed line corresponds to the single frame module, and the solid line corresponds to the multi-frame module. And you see it is always beneficial to have this temporal context of 3 frames. So the detection accuracy is always higher for the multi-frame model, and the localization error is always lower for the multiple error. So it's clearly beneficial to have this frame window of 3 frames. Then how does our architecture look like? As I said, DECODE is a deep learning based fitting algorithm. So here in the beginning, you have the 3 frames, right? And then DECODE basically features like 2 unit-like modules. So in the first one is shared among the frames. So you have a unit basically, and you feed all the frames through the same unit. And then you concatenate the output of these units into a temporal context, which is then, we designed it in a way that it should basically figure out the temporal context of these 3 predictions, which happened here earlier, and you then have your different outputs. So now I would show you how the output looks like. So if you think about it in more of a machine learning, deep learning way, the basic approach, if you do this image to image, would be that you just activate or like try to find the centroidal point of the PSF. And this has been done. So this would now look like in 2D that you have like a single pixel which is active just in the centroid of the PSF. But it comes with a couple of drawbacks. For one is that you are limited, or like your pixelation limits your resolution you can get out of this, right? Because if 1 pixel is 100 nanometers, then you will never go down to 1 nanometer in localization precision, because it's just not possible if 1 pixel has an extent of this dimension. Then if you do it in 3D, you have the problem that your output gets quite sparse. So you need a big output for comparably few numbers of emitters. And of course, you need a 3D architecture, which is more computationally expensive. And the last point is that it's not so easy in this way to have a meaningful uncertainty measure in a way that you can distinguish between the probability of having a detection and how well your detection is localized. In DECODE, we do it a bit differently. We use what we call our subpixel pointers, and I'll show them to you now. So suppose your predicted PSF center is a bit off of the pixel center, right? So this is one pixel here, and suppose this is a bit off. We would then have two outputs. Additionally to this detection, which I've shown to you already, which just contain the value of these pointers in X direction here, and then in Y direction here. And then basically with this method, you can get to, in principle, an arbitrary resolution because these channels could contain any value. It's just a floating number and it could contain any value. So you're not limited to your pixel resolution anymore. And then moreover, we also feature an uncertainty measure, the sigma, which I indicated here, which corresponds to the extent of this function, right? So DECODE also gives you an uncertainty measure how well it thinks it localizes this emitter here, and then this can be easily extended to 3D, right? So you just add another channel for the Z dimension, as illustrated here on the right? So this is one pixel. Those are your offset pointers in X and Y, and then of course you have another one in the Z dimension. What is now really important and not at all always the case for a deep learning method is that your uncertainty measure is actually meaningful. As I already said, our uncertainties are predicted in X, Y, Z and in the photons as well. And what we did here was to have like a high density setting of localization microscopy data. And we did this experiment with the same configuration of emitters a couple of times so that we could get a measure for the localization error empirically. And then we compared this to what DECODE predicted as an uncertainty measure. And you see that it correlates quite nicely, right? So here on the diagonal, you see most of the red points. So you see that the uncertainty measure that DECODE provides correlates quite good to the empirical localization error. And this is in contrast to what is sometimes used, the grammar-raw lower bound, the CRLB. And the problem with this is not so much the definition of it, but rather the assumption you do, because the CRLB is mostly calculated under the assumption of isolated emitters. And there it gives you the nice theoretical optimum. But of course, if you go to high density data, then you violate your assumption you do in the first place. And you see that the CRLB is not really correlating good in this case. Okay, then one step further, you just extract your localization. So you would just look up in the detection channel where you have something, and then extract all the attributes such as the precision and the uncertainty, the brightness, and so on. And what you can then do is you can filter quite nicely with this, right? So you here in this case, I've shown you that you filter, for example, between a probability of the detection between 60% and 100%, and of your uncertainty measure between 0 and 40 nanometers, for example. And this is quite helpful for rendering because then you can like wiggle around and optimize your rendered image. We provide some basic functionality of rendering in DECODE itself, but of course you are free to use a dedicated renderer by just exporting the list of localizations as a CSV to a more sophisticated and dedicated rendering algorithm. With this, I will come to the training procedure, because now this is the interesting thing in a deep learning setting. So how do you actually train this? It looks quite similar to the fitting procedure, but yeah, of course now different, because we start with the ground truth emitters. So what we would do is we would just sample emitters and frames on the fly while we are training. So we have, in principle, unlimited training data. But what we would do is we would sample those emitters at a random position so that we don't have any bias to structure or something. And of course, what you would need to set as a user, you would give us a rough estimate of the lifetime of the emitters and their intensity. So those things with the star are things that you need to give in to the framework to simulate your training data according to your experimental data later on. So then if you have your ground truth emitter positions, you would feed this in to an image formation module. And it's quite crucial that this image formation module is accurate, because if the difference between your training data and your experimental data later on is huge, then you will degrade in performance. So the image formation basically is comprised by two components. One is the PSF, and we use cubic splines in this case. And then the second one is the camera specification. So you would need to specify the EM gain, for example. And maybe already as a short preview, the PSF calibration can be done in SMAP, for example. And yeah, you would just provide the beat stacks and then extract your calibration and can then load this into DECODE later on. But we will show this to you later in more detail. After this, you would just feed it through the network, get your predictions, and then what is else there to say is that our loss comprises three components. One component makes sure that the number of detections is correct. One component makes sure that the localization and the uncertainty is well calibrated. And the last component is making sure that the background, which is another thing we predict, is accurate. Okay, and then bottom line for you as a user, maybe what do you need to provide during the training step? You need to provide us the camera specification, right? So the electron conversion and the EM gain, for example. You would also need to provide us the calibration file, and then some basic simulation parameters. So here you see, for example, a background range where you would like to simulate. You see the number of emitters you would like to simulate on average on a frame, and the intensity and lifetime average. We have seen in our experiments that the exact values do not matter so much, because most of the things are distributions. And then if you simulate the emitters and distribute them over the frames, all of these values distributions are smeared out. But of course, they need to be somehow in a range where your experimental data is later on. And also in SMAP, we provide a way to like pre-fit your experimental data and extract these parameters. But it's of course also perfectly possible to try out simulation parameters, and then if you see that it didn't work at all, then you might need to have like a closer look at them once more. Okay, then coming to the results. As you probably know, there is this SMLM challenge for some years now. And in this figure, we plotted three modalities, so 2D localization microscopy, astigmatism, and double helix. So these are the colors. And each of those points in this figure corresponds to a submission of an algorithm, right? So each of those points is one algorithm. And in an evaluation like this, you can, of course, always trade localization error for detection accuracy, right? So what we did here was we colored in an area basically the surrounding of all the submissions in all the three modalities, right? And you can see that with DECODE, which is here indicated in the bold symbols, we are always well outside of all the other algorithms, even if we consider the trade-off between localization error and detection accuracy. And this is quite remarkable. For example, here in low signal, high density, you see that the distance here in 2D or a double helix astigmatism is quite far between all the other submissions of the algorithms and then our submission of DECODE. Okay, so far for the challenge. And then coming back to the main point, going high density to reduce the acquisition time. What we did here was to image the same site under different excitation. And you see here that in the beginning we are in a single emitter regime, so the distance between those is quite far. And you see, of course, that you get a nicely resolved image out of this. Spatially and axially. And then as you increase the density, you see that the resolution gets slightly worse, but actually stays quite good, right? So if you compare this to this, then the difference is not huge. And we then evaluated this against C-spline, a dedicated high density fitter, and you see that there's a remarkable difference in the signal you can reconstruct out of this. Yeah, so it's quite an improvement, I would say. Of course, you lose a bit of the quality, but given that you reduced your acquisition time by more than a magnitude, I think this is quite usable. And then if you do this to more extent, here you see a LISA example, nuclear pore complexes, imaged in 3 seconds. And this is something that DECODE really enables. And then lastly, you can also go now to ultra high labeling because the problem is if you need to stay in a single emitter density regime is that you usually, as you know, need to pre-bleach and then get those isolated emitters out of it. So it doesn't look really nicely afterwards. But now with DECODE, you can really see that you can resolve this in high density quite nicely. Even the hole in the middle in the axial view is quite remarkable. Okay. Then, of course, if you think about the localization procedure, you will basically see that each of these algorithms must have a limit, or like will behave under super high density in some way that is maybe noisy or that shows you some artifacts. And for our algorithm, we observe that if you have hard samples, and we mean by that they are like super dense, super dim, or super out of focus, that you have sometimes a bias towards the pixel center. So I hope you can see this over Zoom. But sometimes you see here this maybe like a grid artifacts, which are a bias towards the pixel center. Here you can see it maybe a bit better. And then for DECODE, luckily, we have the uncertainty measures too. Namely, we can filter by uncertainty and probability. And you see here on the left is the unfiltered localizations. And then here on the right, the filtered case, where you can see that you can get rid of these artifacts quite nicely by making use of one of these filtering means. Then what is, of course, also interesting is how fast is DECODE during the fitting. And for this, we again evaluated this over quite a range of densities. And you see here the computation time per frame and the two deep learning methods. So DECODE here at the bottom in blue and DeepStorm are linear in the frames. And then a classical fitter goes up by the number, by the density, because you get more emitters on a single frame. And then, of course, you see that if you compute this same runtime per emitter, then with increasing density, the computation time per emitter decreases linearly, and you have like a difference of 3 magnitudes between a classical fitting algorithm, and even more than 1 magnitude between DeepStorm and our algorithm. Of course, a deep learning method needs to be trained before you can use it. In our case, we used like a recent GPU, the RTX 2080, and in most of the cases, you get convergence in under 12 hours with this setup. So here I've depicted an exemplary case of the data we will fit today as well. And you see that even after 3 to 4 hours, there's not really so much happening anymore. And this comes in handy because for the Google Colab, which we will show you later on, you have like a usage limit of roughly 12 hours. But then you need to factor in that these GPUs you get there are usually slower by a factor of 2 to 4. So you are still making sure that you are in a good regime where your model has converged already quite far. And with this, I would already come to almost an end. I would really like to thank Jonas Ries and Anna Kreshuk for the great time I had at EMBL during my master thesis. It was really hard to beat. And then our nice collaboration, namely Artur Speiser, Jakob Macke, and Srini. Here, I think it turned out quite nicely in the end. And yeah, thank you. Okay, so what is DECODE? Again, DECODE is a deep learning based fitting algorithm. It's for high density 3D localization. It enables high speed, ultra high labeling, and lifestyle localization microscopy. And the two components which are quite important are the temporal context, which improves the localization, and that we have sophisticated uncertainty measures that are actually meaningful. And with this, I come to my last slide. So you can find our preprint on arXiv. You can find our the code, which is open source here. And we will later on introduce to you the Google Colab notebooks and the easy installation via Conda. Thank you.
Yeah, thank you so much, Lucas. I think now we can have questions. So you can either raise your hand in your video or in the participants panel, and then I see it. And then you can just ask your question after unmuting. Everything clear? Any questions? If not, then
for also, just using your voice, so it doesn't feel like we're speaking into the wires that are behind our computer. So
I have a question.
Yes, please.
Yes. When you showed the bias toward the pixel center, it seemed to me that it was mostly the vertical center of the pixel. Like the grid was like this. It wasn't really a grid with vertical and horizontal artifact. And I was wondering what is the reason for that, because I mean, if it's a problem of the S over N of the acquisition or the density, it shouldn't be more sensitive in one direction than in another. And also, if that is only one dimension, you can just rotate it and rerun the algorithm, right?
I think in this case it was just like random in a sense that it of course depends on your configuration of your structure, right? So if your structure is really dense in the other direction, you will have it in the other direction.
Well,
so yeah.
I'm not sure. It could be related to the fact that we here use astigmatism. And then, of course, if you defocus, one direction is still much better defined than the other. And then, of course, you would get more often hard sample artifact in the other direction. And see, I mean, you mostly see for the red ones, you mostly see this artifact also for very much out of focus localizations. And I think this could contribute to this.
Yeah, that's from the top. So.
Exactly. Good. Any more questions? If not, then yeah, how should we do it? Directly go to the DECODE example?
I think we have like a short break if the questions are.
Otherwise, there's also a very brief question from Osrat in the chat, and she's asking if we can use this also in fish samples.
Like fish, like the animal, or fish like in situ hybridization? That's written with capital letters, so I guess in situ hybridization. Yeah.
I can answer that question. In our lab, we've started using it for that, and it works really nicely. And so stay tuned. We've been collaborating with Stefan Preibisch at Janelia, and applying it to 3D imaging of fish.
Are there more questions?
Good. Well, I think the questions will come during the tutorial. So thanks a lot, Lucas. That was really a fantastic presentation. And yeah, should we then take 4 minutes break and continue at 2:45? We can all stay online, of course.
So I guess I would start. There's still 29 participants. That's very encouraging. And as you can see, I'm on our GitHub page, and yeah, you can also go there. Just follow the link. It was also posted in Slack. And then I'll start with a fresh collab session alongside you. So first, yeah, my name is Artur, and I also developed this algorithm. And one thing that was our goal when we developed this algorithm, or one obstacle that we had to overcome when developing algorithm is that is that training a deep neural network obviously kind of introduces another degree of difficulty for the end user, because there are many other algorithms where you simply upload your frames, you click one button, and then it starts localizing. But if you have a deep learning algorithm, there's kind of the scary step in between where you have to do some machine learning, and not everybody does that as their day job. So we had to come up with a way to make this as easy as possible. And so one thing we try to do is give everyone the possibility to try this out without installing anything. And fortunately, there's this thing called Google Colab. So if everybody could just go on our GitHub page and then scroll down to the README, and then there's two links. One is DECODE training and DECODE fitting, and you can just open both in a new tab. All right, now let's just hope we don't crash the server or anything. And yes, so for me, they load up nicely. And so this is now also for me a completely fresh environment. So I've run nothing here. And then everyone, maybe before I actually start describing what we're doing, could execute the first 3 cells. And what that means is click on the first 3 arrows next to check GPU access. And then you get a warning. But if you trust us, you can say run anyway. And then there's step 1 and step 2. And you can just click at them. and then it will install DECODE and download some data. And this will take a couple of minutes. So let's do that while I'm talking. You can also already do that in the second notebook. So you have the same titles here, check GPU access, click the arrow, step 1 and step 2. And then it will just do that stuff in the background already. So first, maybe quickly, what's Colab? So Colab is a service by Google, which lets you run code in the cloud. And it gives you free access to, well, to computing resources, and most importantly, also to GPUs. So now for me, it says, I check the GPU access and it says my GPU is Tesla P100. And at least in my experience, I always got a GPU. So I don't know how many they have, but at least for me, they already had one ready. But it is theoretically possible that there isn't one free. But let's hope everybody gets one assigned. The way Colab is structured is it runs notebooks. So I don't know how many of you have worked with Python and Jupyter notebooks, but Jupyter notebooks are kind of a way of programming that became very popular because it makes sharing code and explorative coding very easy. So the regular way how you would normally code is in scripts. So you write a piece of software, you execute it, the whole thing, and at the end you get some sort of output. And in contrast, if you have a notebook, then you have kind of this compartmentalized code or just comments. So you have a sequence of cells, and each cell can contain a little block of code which you can individually execute, and then you directly get the outputs of running that code. And then you can, change it, try different parameters, iterate over it much more quickly. It's also very nice to share your code because you can have these additional markdown cells with nice formatted text. But yeah, I think you will get the hang of it while we are going through this. Okay, so the last time I tried this, it took 2 minutes to install it. Yeah, okay, my installation is done and now it's downloading the sample data. Now, for each cell in the Colab, you can actually double click it and then you see the source code behind it. So here in this first cell, this is just some markdown text. And then if you double click it again, it disappears. And so for this first code cell, if you double click it, here you have some code which imports Torch, which is a deep learning library. And then it checks for available GPUs and it prints out which GPU you got assigned. And this output might be different for you. So they have an assortment of GPUs. Sometimes you get K80s or Tesla T4s. I got a P100 here, but that's kind of random. All right, it now looks like I also downloaded the sample data. Then the next thing about how this works is that you kind of have your local environment, and it is, it's not a temporal environment. If you exit the notebook and go away, it will delete everything. And if you click on the link again, you will get a fresh notebook where you can start again, and you have to also install DECODE again. You can actually check this here. So on the left side, there's this little symbol of a directory. If you click there, you see your local environment. You can actually go up, and then you see the directories of just a regular, I guess, Ubuntu installation. And then content is where we actually work in. Now, if we actually want to work with this, we need some way to provide data that we want to work with, for example, your frames. And of course, we want to save the results. And there's 2 ways. And the easiest is to mount a Google Drive. So if you have a Google account, you can, again, just click on the arrow to execute that cell. And you'll get a link. And if you click that link, it asks you to sign into your Google account. And then you get a code. And you copy that code. and enter it back into your notebook, and you press enter. And what it does now, it mounts your Google Drive. Okay, so now, if we go back here, I have a new folder, which is called G Drive. And here, if I click on my drive, it actually has all my data, which is on my Google Drive. So now I have access to all the data, so I can just upload stuff to Google Drive, and then I have it available here. Or I can save my results in Google Drive and access them from everywhere. The alternative, if you don't want to use Google Drive, is you can simply use this file browser. And for example, here we have the example data, which we downloaded previously, and you can just right-click it, download it. You can also right-click a directory and upload files directly. So this is the alternative without, if you don't want to mount your Google Drive here. Okay, so these are, I guess, the prerequisites, and now we can get into actual decode stuff. So again, to actually train a decode network, there's two things you need. You need a spline calibration file, and Lucas briefly mentioned how you can create one in SMAP, and he will actually show how this is done later on. But for now, we're going to use one that we provide, which you downloaded before. And it's an astigmatism PSF. And the second thing is you need parameters. You need a whole list of parameters that comprise all the information that we need to set up the network. So how is the architecture supposed to look like? What are the camera parameters? What are the and what are the simulation parameters? Okay, any questions so far? Did this work for you? Did the installation and the downloading work for everyone?
So far, it's all okay for me.
Cool. Perfect. So then I'll continue. So again, here you just provide links to a parameter file and your point spread function that you fit before. And once you've made your own ones, you can just, replace this path with a path to the files you have in your Google Drive. So that's the idea of it. And now, once we start training, of course, we also want to store the output somewhere. And then there is, again, you can store it locally. So right now, the path we chose here is network. So we'll just create a network directory and then store everything in there. Or you can go on your Google Drive. And I already made a directory, which I call DECODE tutorial. And you can just copy the path from there. Or it will make a new directory in there. So you just copy this path to your Google Drive, then choose a name for your folder, and it will create that directory, and then everything will be put in there and will be uploaded to your Google Drive. Okay, so Lucas already mentioned what parameters we care for mostly. And we can just take the parameter file, which we already loaded, and take a look at it. So if you just jump over this cell and execute the next one, then I got an error because I didn't run that cell yet. All right, so here it goes. So this is a directory that contains all the parameters that we use during training. And it has different subcategories. So there's camera. This is what Lucas already mentioned. It has evaluation. So this is the settings that we use for kind of evaluating performance during the training. It has hardware parameters and so on, hyperparameters. And again, our goal was to actually make deep learning accessible to everyone. And the nice thing about DECODE, as far as we experience it so far, is that it's very robust to well, not to hyperparameters, you have to set those, but to different data settings. So these parameters should basically get you all the way, and you should not have to change any of them in 99% of the cases. So you can forget about most of them. You can just close the output again by clicking on the cross here. And there's a few parameters that you have to set, and we'll go through some of them here, and then later in the second practical session, we'll go through them in more detail. So one thing that is important is, of course, temporal context. We talked about it, why it might be useful. So here you can choose if you want to use temporal context or no. And again, in a regular setting, we found that temporal context is almost always beneficial. But of course, maybe you know something about your data why it might not make sense. I guess one scenario where temporal context does not make sense is if you do particle tracking, or at least you have to need to think harder, because of course, in that case, your particles move from frame to frame. So you don't want your network to learn that they are actually in the same position in adjacent frames. Then another setting is the emitter average. And this number sets the number of frames in a 40 × 40 sized patch. So this is what we use during training. And this is independent of how your actual test data looks like. So if your test data...
I'm sorry, Artur.
Yes.
I have a question. How do I get these model files?
Excuse me, I didn't get it audibly.
So I'm trying to follow what you're doing here.
Yes.
And I have to put the path to the model .pt files, right?
Oh, are you in the fitting notebook?
No.
Because here's the model file, but we are in the training notebook. You don't need the.
In the training notebook, there is the parameters for training, and the first section is inspect parameter and adjust path.
Exactly. Yes.
Right. So these, I need the path to these files, but these files are on your Google Drive, not mine.
Oh, exactly. So the first two files we downloaded before. You can keep them like that.
Yeah, I have put them, but the model dir path, the third one.
Yeah, that's just for the output. That's where you want to save the model that we get later when we start training.
Okay.
So you can just keep it to the basic setting network. Then it just gets saved here locally on the machine that Google Colab provides, or you use this path below here, and then you just choose a name for the directory, and that will get created in your Google Drive, and then it stores everything in there. Right. Okay. Any other questions right now? Okay. So again, the emitter average tells you how many emitters get simulated in a 40 × 40 sized frame patch. And again, we always use this size during training, independently of how big your data is. So maybe your data is 200 × 200 pixels, but that's fine because our network is fully convolutional. It works on files of different sizes. So it kind of adapts to the size of your data set, and you can run it on any size. Now 25 is pretty dense, probably denser than what you would use normally. But that's kind of fine because our network kind of needs to learn to deal with the most difficult conditions. And then, you know, the easier conditions where you're well isolated emitters, it will learn anyway, because this will show up too in some frames. And then there's another parameter. This is the range of emitters in actual direction. So this is the range. Yeah, it's pretty self-explanatory. So what is the range in which your emitters, or you try to localize your emitters in the axial dimension? And this purely depends on, you know, what PSF you use, how good your microscope is. You should just choose a range that where it is realistic that you can actually pick up localizations. So if you set this to 2000, then you will just generate data, or you will just generate emitters that you can't localize anyway because there's no signal. So that makes no sense. And usually, for example, here for astigmatism, something between 600 and 800 nanometers in both directions makes sense.
And maybe to add, yeah, of course, this should correspond to your calibration, right? So we will later see this. Typically, it's sufficient to just put here the limits, or maybe with a slight buffer of your calibration.
Yeah.
I have a brief question here. Now, of course, you're doing astigmatism. If you want to do 2D localization, you also have to put your actual direction range for the autofocus information?
Yes.
Okay.
Yeah. So Lucas, do we always use beat calibration for 2D data, or? Yeah. Okay.
Yes. As it is implemented right now, and maybe also related to the paper of the lab of Jonas, you can even predict 3D out of 2D data, but you need the calibration for this.
Okay.
Still on the calibration file, is there any specific file format, or?
So in general, you could use anything that gives you cubic spline coefficients. The most convenient thing at the moment is to do it via SMAP. But I think you, Artur, have also tried it to do it via C-spline, which is also possible.
Yeah. This is not fully supported by us yet, so this requires a bit more work. Yeah, we also tried to come up with a spline fitting that would work purely in Python, so it's more seamlessly integrated into the workflow. But kind of an advertisement for SMAP here. If you use it, it comes in handy at different places. So first of all, you can fit your PSS with it. You can also use it, as Lucas mentioned, to fit your simulation parameters. And it also has some nice tools for rendering. So yeah.
And maybe there's one question. If the input size of the frame is bigger, is it pulled down to 40 times 40 pixels? And that's not the case. So basically what we mean that it's independent of the input sizes, not that we rescale the image, but rather that we, like the network will just like slide a window literally over the input frame, and therefore it doesn't depend on the size of your input frame. So there's no loss if you, no matter how big your input frame is.
Yes. But it will, of course, be slower. So the bigger the frame is, which is not really the case for this other algorithm, where it only depends on the number of emitters. For us, the overall size, like in the frame dimension and in the XY dimension, makes up the speed. So the bigger the image and the more images you have, the longer it will take. Okay. So let's continue. There is some other parameters you might want to change or have to change, and it's pretty easy to change them. So again, if we look at our parameters and you have the urge to change one of them, you can simply check how it's called. So let's say you want to change the background distribution. Then you see that the background distribution is under the header simulation. It's called background uniform. So you can simply put in param.simulation.background uniform and put in the range, and this is how you would change that parameter. And you can do that with all the parameters in here. And again, I will go through some additional parameters later in the second part of the tutorial. Now, if you want to provide your own calibration file, so you went into SMAP, you provided your own beats, you fitted your PSF, then here is the place where you can put it in. So you can uncomment that, then you probably stored it somewhere in Google Drive, you put in the path, you put in the name, and this is how you would change to a different calibration file. But for now, we keep everything like it is. And now we can look at how our simulation looks at this point. So we click at that cell, and it will set up the simulation. You can look at the code. Again, if you double click on it, but again, it basically just takes in the parameter file and then sets up a simulator. So we initialized it now, and now we can look at an example. And there we go. So I hope this works for everyone. So this is one frame that our network uses to train, well, to optimize its parameters. So again, it's a 40x40 patch. We have here the ground truth positions, and then you see just random emitters in random Z positions with different intensities. And then we can go to the next step where we set up the training process. And this includes several different steps. So we set up the logging. Logging here means storing parameters during training so we can track the progress. It sets up the actual network, the optimizer. So the optimizer is basically a scheduler that performs the parameter updates, the loss function, and so on. And then the next, I already did that. Okay. So it says training set up successfully. And now we can actually, before that, we checked the simulator and we created one frame. But because we use temporal context, what we actually use during training, again, is such a sequence of 3 frames. And here we see all the ground truth positions that get activated throughout these 3 frames. And again, you see that sometimes you see, for example, here an emitter only in the middle frame. So this one was not active in the adjacent frames, but then, for example, this guy down here is clearly activated in these 2 frames. And so our network wants to use information from this frame also to produce the best possible localization in that frame. Okay, that's basically it. So we have our calibration file, we set the parameters, we set up our simulator using those parameters, and we can start training. Now the first point here is a cell which is called resume training, and you can ignore that one for now. So this just is a tool in case you already started training before and it didn't finish for some reason, maybe your internet crashed or something, but you still have your checkpoint file in your Google Drive, then you can put in the path here and it will continue training from there. And this is also useful because, again, Google Colab puts a limit on the time you can use a GPU. So if you didn't get it finished, you can continue it in another session. I guess that should work, right? Right. Then we get to another nice tool that we use, which is called TensorBoard. And TensorBoard is a tool that gets used by many deep learning researchers because it's just a nice way to track your training progress. And what that means is that while you train your network, you hope that the performance gets better and better, the more closely you get to, to the best parameter setting. And this gives you a way to check if everything goes as expected. So you can simply execute that cell, and it will give you an empty TensorBoard. And it's empty because we didn't do any training yet. And then finally, the last cell will start your training. And the outputs you see here, well, they mainly tell you that something is happening, which is always good. You have here the epoch. So we're in the first epoch. We are going through 156 batches in every epoch. And you see the loss function, which hopefully will go down. And it basically iteratively does an epoch of training, and then it does a test run on some data. And from that test run, we will get some performance metrics that we can then look in look at in TensorBoard. So we will let that sit for a while. I hope this runs for everyone. So everyone got a GPU, I guess. That means this is already good to know. And during training, you will get these warnings, which you can safely ignore, and we might get rid of them eventually.
So what are the best GPU we can get? I mean, how do we know if we are lucky or not, depending on the GPU we are assigned?
Actually, yeah, maybe you know more.
What is it? There's the T4, there's the K80.
K80.
Yeah, I actually got a P100, which is 16 gigabytes, which is pretty large.
Yeah.
So that's a lot of memory, at least.
But what we could do is we could just compare how long it takes for one epoch. And that would be a nice thing to compare among the participants.
So I have a P4 and it hasn't finished the first epoch compared to Artur, who is already on epoch 3. So
that's like,
I guess.
So what is the time estimate for you?
Where do I find the time estimate?
At the bottom in the progress bar in the bracket.
Yeah, so for example, for me, it does 4 iterations per second. So 4 batches per second.
Oh yeah, I'm like, it's better for, it was like 1.5 or something.
Okay.
Yeah, so I'm also unlucky.
But maybe everyone can give a thumbs up if it works for them,
with
so
the
that we know the general success rate.
Yeah, with my T4, I'm at 2.5 iteration per second.
All right.
Yeah, it's the same for me.
Wow.
The T4.
It's like a mini game.
Can I ask you a question about the GPU availability? So I guess whenever you get one, you have it for 12 hours. Is there a limit to how many times you can use it?
Yeah, go ahead.
So it's a bit of a black box and magic of Google. So once I tried it too often and trained quite a lot, and then they kicked me out for a day or two. Could only use on CPU, but yeah, at least to try it out, I think it's perfectly fine. But of course, if you are to like run it 24/7, then at some point they will say it's too much. I think in the US you can subscribe to Google Color Pro, then you get more hours and better GPUs, but that's not available in Europe or outside the US.
Is it available?
How much faster is it?
Pardon?
Is it available if you have a VPN to connect to US?
I don't know, to be honest. But I mean, the overall goal of this is to give you like a really low burden access to DECODE and to try it out a couple of times. But then, of course, if you want to really use it in like, let's say, productive environments, you would use your local workstation or your GPU cluster or something which you have available.
So just quickly, so far I think we got 6 thumbs up. So does anyone have, I don't know, an error message or didn't get a GPU or couldn't run it at any point? That would be very useful for us to know. So.
Yeah, one word to TensorBoard. Maybe you need to sometimes refresh it.
Yes, exactly. So yeah, that would be my next point. So now that I went at least through 7 epochs, we can check how if we made any progress. And to refresh, you go on that round error, and then you should switch off the smoothing because it kind of is weird. And then you get a range of performance metrics that tell you how you are doing. And we can, we can go through them. So first we have efficiencies, and we always talk about axial, lateral. So axial is in Z direction, lateral is in XY, and volume is in all 3 dimensions. And the efficiency is basically a measure that they came up with in the in the localization microscopy challenge, and they just try to put all the measurements into one number. So basically, it's a performance metric that tries to trade off the Jacquard index and your localization error and put it into one number. So the higher, the better. But if you are more comfortable with looking at the Jacquard index, we also plot this here. Then we have the mean absolute distance, again, axial, lateral, and volume, the root mean squared error, the recall, and the precision. And then below we have the loss. This is just our loss metric, and this should go down, which it does in this case. And this gets evaluated at every batch. So here you have 7 epochs, and after each epoch you evaluate this metrics, and then for each batch you evaluate the loss. There's also a second header, which is called images. And there, if you really know, if you really want to get into the bowels of DECODE, you can actually check the output distributions of the different channels. You can also look at example frames. So here we have, for example, one example frame that we sampled and ground truth and our localizations. I think the localizations are in red, right? And the ground truth is in blue?
The other way around.
Okay, the other way around.
So it depends on the EM match. You see the ground truth in red, and then the line from the prediction in blue to the ground truth, basically.
Yes.
Also in 3D. And the total output you see on the other frame, on EM out tar is this, but that's not so important. Yeah.
So now there's one catch with this, is that all of this is evaluated on the training data, right? And the training data is simulated, and there we have the ground truth. So this in itself is not enough to tell you that the training goes well, because it might go well on your simulated data, but if your simulated data looks nothing like the real data, then your final results won't look good. So this is mainly a sanity check. This will tell you that the training goes as expected. And there is cases where this might break. So if your loss does something ridiculous, it's like at 1 million, and it stays at 1 million for 2 or 3 epochs, then it probably won't go down at any point in time. So that kind of means that your training went wrong. And this can happen in certain cases when you try to train under very difficult conditions. So very high densities, low signal. And then you have several choices. If you are convinced that this is the settings you want to use, because this is how your data looks like, then the first thing you should try is just restart the training 2 or 3 times. And that might fix it already. And you will quickly see if the loss goes down, then your training performs as expected, and then you will see results. If that is not enough, then probably your conditions are just too difficult. And it's just not possible to learn from the images you provide. And then you have to either, lower the emitter density a bit or increase the signal to noise ratio. But for a regular setting, this should normally not happen. Well, I hope it didn't happen for anyone. Okay, so again, this is for simulated data. And yeah, exactly. One more thing you can try is lowering the learning rate. So we want to use always the highest learning rate possible because this gives us the fastest convergence. But this is another thing you might try if your training does not converge, is lowering the learning rate, maybe to half or to 1/10 or so. Okay, so now we have to check if how our results actually look on real data. And you can just keep training if you want to, and then look at the results later on. Oh, okay, I actually disconnected from the other notebook. So we can then go and reconnect. And now I have to actually install DECODE again. It might be the same for you. yeah, so you can't stay idle too long in your notebooks or you will get disconnected. So we go through the same first steps. I won't mount my Google Drive here, but you can do it to actually use the model you trained before. I will use the pre-trained model so we can actually see how the final results look for that data set. And then later on, I will also show you how the results look with a network in progress. But this will just be a little bit faster. So again, we install DECODE, we download the sample data, which is the same. We provide the parameter file, which we use to train our network, and the model file. And again, I provided, for the previous training, I provided my Google Drive. And if I check my folder, then I have a couple of files here. So first I have the parameter file, and I have 3 model files. And these just get written to iteratively. So after each epoch, we either write to 0, 1, or 2. So it doesn't matter too much which one you use. This is just kind of a safety measure. And then you also have DECODE checkpoint. And this is the file that you provide if you want to continue training after you stopped it in between. All right. So if you keep it like this, then you will use the model that, again, we provide, which we fitted before. And it says model instantiated, so it loaded all the parameters, all the network parameters into our model. And then if we load the checkpoint file, we can actually look at the metrics. So here in the TensorFlow, in the tensor board, you can actually, for example, you can look at the recall. So we are now 18 epochs in. And if I refresh this, then my recall is at 0.4. And now we can choose different metrics here. So this is a completely trained model. And if you look at the recall here, then we are basically here at the beginning at 0.4, and it will keep improving to like 0.6 or so. You can also check other metrics. So precision won't change much. Precision tells you how good you are at avoiding false negatives. You should always be at like 99% or so, or 98 maybe. And yeah, the localization error will hopefully also, okay, this actually is kind of constant, because in the beginning you only go for the easy and very bright and well isolated emitters, and then you keep increasing the recall, and in this case the RMSE stays kind of constant here. Okay, so now the next thing is we actually get our frames, so our test data, and this is this ultra high density data set that Lucas showed in his presentation, I think. And then we have another cell which is called, well, actually, let me talk a little about, let me talk a little bit about the frames. So here you can provide your TIFF file and load it. And if you click on the code, you will see that this got loaded into a variable called frames. And so you can, if you know a little bit of Python, you will know how this is just simply a tensor, a PyTorch tensor, which is very similar to a NumPy array. So you can, for example, check how big your frames are, or what the dimensions are. So you see we have 20,000 frames, and they have the shape 180 times 179. So what I did here is I included a new cell, which you can do. You can either do insert code cell, or you can, sometimes it pops up here, if you, yeah, here plus code. So this will include a new code cell. And then you can, for example, type in frames.shape. So our frames are, we have 20,000 frames, and there are 100 times 80 times 100 times 79 pixels. And this is actually a little bit big. So to analyze it all, it would take like, I think the last time it took me like 6 minutes, but we've already seen there's certain differences. So maybe we kind of want to cut this down. One thing you can do is you can check what to expect with imshow. So if you type in PLT imshow, and then you do frames, and then you take the mean over the image dimension. So this would be the line PLT imshow frames dot mean, and then in brackets 0. And then this will basically give you a low resolution of your structure, a low resolution image. And let's say we just want to focus on this piece down there, so that the image processing also runs a little bit faster, because otherwise, again, everybody has to wait 10 minutes. And the way we would do this is we just cut our frames down a bit. We use all the image frames. That's the double dot, the colon. And then we use the last 60 in the Y dimension and the first 60 in the X dimension. So this would give us this square. So you can just copy this, and then running the frames will be a bit faster. You can also run it on all the frame, on the whole frame, of course. Okay, so let's execute this. The next cell says specify camera, and I won't go into detail here because we will simply use the same camera parameters that we use during simulation, and this is what you will mostly do. And we wanted to keep the possibility open that you actually, you trained a model, and then you want to try it out on data where maybe your camera settings are a bit different. For example, you have a different scaling parameter, which is the EM gain, and then actually you don't have to train a new network. You simply have to change the scaling, and this you could do here. But in this case, we keep it the same, so we just use 50. Then we set up the processing pipeline. So this is the this will control how our network takes in the images and applies our network to them, and how it then combines the outputs and filters, well, the actual candidates. And here again, this might be a good estimate of how good your GPU is. So again, for me, I have to go through 313 batches of data. So again, we have 20,000 images, but we kind of split them into smaller batches and then feed them to our network. And my GPU manages 7 batches per second. And so the whole thing doesn't take too long. And I see that I'm already 45 minutes in, so, but I hope this is useful. And the next thing is, now our network has run, and we can check the output. Now the output is what we call an emitter set, and this is just a class that we wrote, which we wrote with the goal to make it easy to deal with, well, with the outputs of a localization algorithm. So we can see here our network produced 640,000 localizations. We have the pixel size, we see the frame range, and we see the span volume. So this is the maximal extent in X, Y, and Z where our algorithm found localizations. And we can now check a random frame. So this will give you a different output each time you execute it. And so here you see what our algorithm did. So here you have one, and now this is actually real data. So this is a real data frame. And it's maybe not as dense as our simulations, but pretty dense in some parts anyway. And you can see where our algorithm thinks that there are emitters. And the colors in this case indicate the probability that it assigns to those emitters. So for example, here you see a very dim signal, and so our network assigned it a low probability. So you might throw that one away later on. Let's check some uncertainty estimates. So again, we have 640,000 emitters that we found, and this is the frequency of different detection probabilities and sigma estimates in X. So again, one big advantage of DECODE is that we get useful uncertainty estimates. And here we see the distribution of it. Now for the detection probability, most of the times DECODE assigns a very high probability, and this is actually also desired. So filtering by the detection probability in our experience is not really critical. So you don't really have to change that parameter. You can set it to 0.6 or 0.7, and it won't have a big influence. But the sigma estimates are very, very useful because they give you very tight control over what localizations you want to keep and what you want to throw away. And we think that this is a big advantage to many other algorithms. I don't know, maybe you have worked with a different algorithm like C-spline or any others, and there you also have parameters, but they're called, I don't know, there's either some localization radius or some certainty or something, but these are all parameters that you can't directly interpret. While here it is really a number that is tightly controlled with the true localization precision. And so now let's look at our image, what we actually produce. And if I execute this here, and because I cut down the frames previously, this doesn't really make sense because we produce a too big of a window. So if you also cut down your frames, you want to replace the 160 here maybe with 50 or so. And then you get this image. So again, it would be nice if this was colored in the Z direction. We are about to implement that function, but again, we didn't put much priority on implementing fancy rendering functions because we think that there's a lot of them out there which you can use. Anyway, in this image, we show all 640,000 localizations that we found. And this gives us a decent image. However, it's almost, or it is almost always useful to actually throw away some of them. And this you can basically see here in this distribution of sigmas. So you have this large peak at around maybe 50 nanometer localization uncertainty, and then it goes all the way to 100. So we probably don't want anything above 50. And depending on how many localizations you have, you might throw away as many as half of them or even more. So here we made these nice sliders where you can exactly set your thresholds. And let's say we throw away everything above 30 nanometers in X, 30 nanometers in Y, and 50 nanometers in Z. And again, the probability thresholds doesn't really matter, so you can just keep it at 0.6. And then if you execute this, you probably again have to change the range here. Yes, so again, if you can change 160 to 50, and then execute it again, then you will get a new image. And now if you directly compare it, well, you would have to really zoom in and compare one specific detail, but it will make a difference, and this will definitely look better. And down here, you can actually see the range that we kept. So the green areas is everything that's within the green areas are the emitters that we kept, and everything else we threw away. And this are just the numbers up here. Yes, that we set here. So And what you also nicely can see is, for example, how good your PSF is at giving you the actual position. So here we see that Z has a higher uncertainty than X. And this is, well, usually the case. Normally you have a better resolution in X, Y than Z. Okay, so now, obviously the important question is, how do you choose these parameters? And the thing is that this will always kind of be, well, this will be your decision in the end, because the final product of our program is a rendered picture, and you want to have a picture as nice as possible, and only you can decide what that means. So if we keep throwing away localizations, so let's say we go to 20, or let's say 15, 15, and 25 nanometers, then at a certain point we will run out of localizations. So in this case, we have a lot of them. So we still get a decent image, but you already start to lose some of the structures. So again, you kind of have to find the right compromise between the number of localizations you want and the error you want to accept.
Maybe one thing to add there, if you decide to go for a dedicated renderer, you would of course not filter anything before you export the emitter set, right? Because, for example, in SMAP, you can filter dynamically during the rendering, so you would just export everything to a CSV file and then do it dynamically, because most of these renderers allow for filtering in the rendering step.
There's also one fancy way of rendering that you can use is if you take each localization and then you construct a Gaussian blob around them with the uncertainties that we provide, and then you create a huge 3D histogram out of that, then you can use all the localizations again, because the uncertainty is kind of part of the rendering. And then you will get a nice image out using all the localizations, but this is kind of computationally expensive, rendering like that. But this is also something you can do. Okay, so then the only thing that remains is saving the results. So when you are happy with your emitter set, if you filtered out what you, or if you, well, again, as Lucas said, you don't want to filter out anything if you want to render in a different program, then you can just save your emitter set. And the easiest option is just a CSV, which can be read by basically, well, you can load it into Fiji or SMAP or anything you like. Okay, I think, yeah, I'm far over time, but I think this was all important. And I hope this worked for everyone. If not, it would be really, really useful if you give us any feedback where it didn't work for you, what was hard to understand, what we could improve, so that our next iteration becomes better. Thank you for your attention.
Have you tried it for different type of single molecule techniques, like DNA paint, Storm, Palm?
So far, we've definitely did Storm. We did DNA paint, and we got great results on both. Again, Srini is working on fish data. What else have we tried so far?
And is the fact that between techniques, the on-time change, is it something that might impact the learning?
Excuse me, I didn't get that. Can you repeat the question? The last one?
Oh, yeah. Yeah, I was wondering if between, for example, between Storm and Paint, the on time of each flow for is completely different. So I was wondering if it changed the training also.
So far, we've basically applied the network unchanged to these two imaging techniques, because while the inner workings of the imaging technique are very different, or how the paint molecules bind to the molecules and anything, the end product, so the frames that we use, have very similar characteristics in our experience. So we didn't have to change much at all, actually.
Well, what you should change, of course, is the intensity, because if you in DNA Paint have 10 times as bright emitters than in Palm or Storm, then you would want to put this into the training.
Cool, thanks.
Cool.
I have a question, if it's possible, on the type of camera that you use. So for now, first of all, you simulate with a smaller camera frame than you do your predictions with, which works great for EMCCDs, but not so much for CMOS because you have this pixel-dependent noise. Is that anything you thought about, worried about, or working on?
So I've worked on one data set with a SCMOS camera.
Mm-hmm.
And there, well, we can use our simulation setup also for a SCMOS camera. We basically, right now, we only set the EM gain to none, and then you're good to go for SCMOS cameras. The pixel-dependent noise and the variance I also put into my simulation. It's currently not implemented in the code. This is something we still have to do. So you can apply it to SCMOS data, and I think you will get decent results. But that last bit you get by actually providing the pixel-dependent noise that is currently not yet implemented. But I think this shouldn't be too difficult, and we will probably implement it eventually.
All right. Thanks.
Yeah, maybe one comment to Gregor, TensorBoard. Yeah, so somehow this Google Colab thing sometimes breaks TensorBoard, but it doesn't have an effect on the training. So you can still, for example, check the convergence via the checkpoint in the fitting notebook. Yeah, I don't really see anything we could do there, to be honest, but yeah. I think for you it's working nicely, right?
Yeah, for me, I had a.
Yeah, but locally it's stable, so that's yeah.
So again, what you would do then is just supply your model file, or no, your checkpoint file here, and then you can plot the metrics with this.
Yeah.
So where do I actually save my model?
Yes.
I'll just quickly show that, but you can already, if you have any other questions, go ahead.
So maybe I can ask a question in between before we go to the next break and then the local session. Did the local installation work for everyone? Because this would be something we would try to solve in a break if someone has problems there.
I think Alvaro mentioned in the Slack channel that there were some issues with Linux. If you could maybe address that.
What was the?
It was a bit.
Let's see it right now.
So it was written. I followed the installation instructions and everything went fine, but I cannot see the environment on Jupyter, although it's on Anaconda. The same thing on my Mac works fine, but I have a problem with Linux.
Oh, okay.
Can you find it?
Yeah.
Okay. Or maybe he could unmute himself and ask the question as well.
Yeah, I think I know what the problem is. Maybe I contact him directly.
how far along are people? Has everyone managed to run the Google Colab notebooks up until this point? Great.
Yeah.
So how many of you have not gotten it to work or have any issues?
So it's working, but the tensor board is only displaying like the 4 first epochs, whereas I'm already at like 18 or 20. So I cannot really see the evolution of the training.
Okay.
You might have to rescale the axes by hitting the blue square button.
Yeah, or you can just double click it.
Oh yeah, right. Okay, that's good now.
Okay, cool. Yeah, so this is actually very very nice that it seems to work for everyone.
So when do we stop the training? I mean, what is the criteria here?
Well, the nice thing about it is that because we use simulated data and we don't, so other algorithms, what they do is they, for example, sample 50,000 frames and then run it on that. But we sample new data at every training step. So we can't actually overfit to the training samples. So whenever you stop your training, you can't stop it too late. You don't have to look at any validation loss or anything and look out for overfitting. So this makes everything much easier. Right now, I think we set it to 10,000. What's the number of epochs we set it to? I think 10,000 or something. Yeah, so this obviously would take a long while. And it's probably not necessary to train it that long. If you train it for the 12 hours that Google Colab gives you, this will get you a decent model. And then you could restart it again in a new session and continue training for a little bit longer. Again, it's much faster on a better GPU. But after 12 hours, you should have a decent model that probably has, I don't know, it's hard to quantify, but probably 95% of the performance that you would get at full conversions. And after, let's say, 24 hours, you should be done in any case. Let's say.
The typical number of epochs you run is 25,000.
At 10,000.
10,000.
Yeah, but that's really generous. So this just to make sure that we get everything out. 5,000 should almost always be sufficient, I guess. And again, you don't have to wait till the end to actually try it out. Later for the local installation, I will plot something in between during training, and then you can see that even after, I don't know, 20 minutes, you already get a result that is presentable.
And if you do it locally with let's say your card is a 2080 Ti. As you said, so how much time does it take to do these 10,000 epochs with the classical training setup that you've shown here?
12 hours.
12 hours will give you these 10,000. Okay.
Yeah. So actually, apparently, I'm off by a factor of 10. So 1,000 epochs is what we're looking for. Sorry.
Okay.
Yeah, so on the RTX 2080, I get like quite exactly 12 hours for 1,000 epochs. So.
And of course, there's a third possibility. So you can do it locally, you can do it on Google Colab, and you can also use other cloud services like Amazon Web Services, and there you can, get all the hardware that you can pay for and use that. That's also always a possibility.
And how flexible it is to different acquisition? I mean, if you use the same microscope, the same objective, So assuming you have a pretty much constant calibration curve, which is optimistic, but let's say you do that for one microscope, one camera, one acquisition style. Is that flexible for then all the acquisition from that microscope? Will you have to train only once, or is it better to, because it's simulated, right? So it does.
Yeah, exactly.
So you can retrain.
One example we can give you is during Lucas' presentation, he has shown these 4 data sets for different densities, where you look at the same specimen, but you tuned up the intensity of the camera, and these 4 data sets are all fit with one model. So for example, it does generalize over density. So the only thing that is important is that your PSF doesn't change too much.
Okay, so if the calibration changes, basically you have to retrain.
Exactly, but if it doesn't, then your network will generalize in general. Yeah, in general. So yeah, you don't have to retrain in that case.
Okay. And that means also that if you have several colors, like channels, you should train for each of the channel separately. I see Jonas saying yes.
Yeah, I don't have experience with that, but maybe Jonas.
Good. Any more issues with the local installation before we go to the break?
Yeah, but I mean, you can also write us during the break.
Yeah, sure. I mean,
I had a question along the similar lines of transferring training sets. You guys ever try with the simulated PSF? Like you just simulate a standard Gaussian PSF and try to run it across.
So yeah, for example, a simple Gaussian PSF does work pretty well for 2D data. And many other algorithms, for example, use like an elliptic Gaussian to fit astigmatism. But we did not implement that because this will always cost you performance. Like getting the PSF right is actually, we found very critical for getting performance. And so simplifying it by using some parametric model is not really worth it. And it doesn't gain you any speed or so. I mean, you don't have to do the bead fitting, but I think most labs do that anyway. So we kind of, we take that as a prerequisite for now.
Yeah, so
I
just asked because
just for a single molecule fish, when we've tried this, we've done it completely without any calibration data. So in principle, for at least when you're acquiring 3D volumes, you can estimate the PSF directly from the data, and that's something that's worked nicely. For this form of microscopy, though, it's helpful to have calibration data ahead of time.
I'm definitely thinking of it in the case that you're mentioning, Srini. You might have data that you may not necessarily have good calibration data for it. And try to just pick out single molecules in maybe in a less challenging case than the high density application.
So I think it would not be too much of a work to simulate or to use a simulator using Gaussian range. And that would work, I think, quite well for 2D data. And it's something we could consider re-implementing. I think it was there at the beginning, and then we are not using it anymore. But it could be a nice addition for the future.
Yeah, so,
but yeah, if you think about that specific
you don't have
setting, you should get in touch with Srini, who's working on that. Exactly.
Yeah. Well, related to that, this is really for EMCCD, but is there a way to reconfigure that if you're using a PMT, for example? Or to bypass these parameters? Yeah.
Okay, yeah, I don't know what kind of camera that is actually. So someone has
PMT is a single point detector from a confocal microscope. I think the PMT is pretty much like an CMOS camera, just without pixel dependent noise. So you would just turn off the EM gain and put in the noise of your PMT in the simulation. Should work.
Should we then have another break until, yeah? Maybe then let's meet in 15 minutes at 1/2 something. Yeah, one thing I would post a link to in the channel to download the raw beats for calibration. This you could just click on. Yeah, before you go into the break. And of course, if you have any installation problems, then also let us know.
All right. See you soon.
Good. Should we continue then?
Yes. So one resource we would like to mention, if you are planning to use DECODE in your productive or like in your lab environment, is our documentation, which gives you some detail about the installation, and also like a short tutorial how you can use the software, and we also provide some FAQ should anything not work. Yeah, and so I hope right now that most of us, if not all, have the working installation, and I would recommend to check that if you go and open up your terminal, and then you can write conda env list, and with that you should find your DECODE environment here in this list. Yeah. So this should work on Windows. It might be a bit different. I think there you go to the Anaconda navigator, open up your terminal there, and then you can do it basically in the same manner. So once you verify that this is the case, you should activate the Conda environment. So Conda activate, and then DECODE env in this case. Yeah, maybe you can check the version. It's just optional, but so that you've seen it. Here you would see, if you just know the list of all packages you have installed in this environment, and here you see that DECODE is version 0.94 in this case. Okay. Always rings the bell when I'm in an online meeting. I'm just going to ignore it. Okay. And then what we now do, we want to copy the example notebooks, and we have put it here in the tutorial. Right, so after you have activated the DECODE environment, you just copy this command, and now set your destination path, so where you want to have your example notebooks. This could be anything, right? In this case, you can put them to documents, and then DECODE, whatever, wherever you want them to be. And then if you press enter, which I'm now not going to do because I already have it, DECODE will load the notebooks in the respective path. Maybe I'll wait a second for this. Okay.
I'm sorry, is there a place where you have these commands that we can just copy and paste?
Yeah, it's here in the tutorial. There you have it.
Oh, yeah. Okay, so that's tutorial. Okay.
The second thing that always happens during virtual meetings is an impact drill with the neighbor. Good. I'll just wait for a bit. And then in Linux, you could check if the copy worked by just checking what is in there, but this is completely optional. After this, you should start up your Jupyter instance. And this, in most cases, would just be this basic command. Just make sure that you run it from within this DECODE environment again, so that you have the correct Python environment. And now the plan is that mainly Artur will give this talk, but I will shortly give you an overview of some basic functionalities and commands you need in DECODE and how to get to your beat calibration. So is everyone happy if we continue? You can also always make use, if you click on participants in Zoom, and then you have the options, yes, no, go slower, go faster. So if you have some feedback, then you can also make use of these. So I don't type this now because my workstation is a few hundred meters away, but you will just say Jupyter Lab, and then your browser will open and you will have your Jupyter Lab, which should then look like this. So within this Jupyter Lab, so this is a collection or like an instance where you can nicely view and run your Jupyter notebooks, so the notebooks of DECODE locally on your computer. You just navigate to where you have stored these notebooks. In my case, it's documents, DECODE Cornelia workshop, and there we have them. And then you should open the introduction notebook. And then you should see something like this. I hope that's visible for everyone.
I'm sorry, how do you open that in Chrome?
Did some browser open up for you, or? Yeah,
no, I have Chrome open.
No, you need to open a terminal and then just say Jupyter Whitespace Lab, and then press enter, and then it will open up.
Oh, I see.
But for example, if you close it, you can also reach it via the address up there, localhost, and the default port is 8888.
Yeah.
Oh, great.
Yeah.
So.
Okay. So here you should now see the introduction notebook. So just double click on the introduction. And in case you have some fancy installation, make sure that you are in the correct DECODE environment. If you followed the instruction like on the web page, you will not have this option, but you will automatically be in the correct environment. And then what you can do is you can just run the first cell by pressing Shift and Enter, or pressing play, I think. So what you will do here is just import DECODE, some more sophisticated utilities, and Torch, PyTorch, which is the backend basically of DECODE. What you can always do if you need help on something, you can literally So I'm creating here a cell. You can literally say help, decode, and then emitter set, and it will print you basically the documentation of this class we are using, so of the decode emitter set. So here you get the arguments you can feed in. But if you want to have it a bit more nicely, you can also go to our documentation, search for emitter set in this case, and it needs a second. And then you can click on the emitter set and you see the parameters you need to feed in to create, or like how to use this, what you are looking for, basically, right? So here in the case of the emitter set, you have XYZ coordinates, and they are expected to be of size n times 3. And then the photon count of size n, and so on. So if we now, close this for now, if we now want to construct an emitter set, that's quite easy. So what you would just say, decode emitter set, then you provide the XYZ coordinates, the photon count, the frame index of these respective emitters. You say which unit you are talking. So this XYZ is now in pixel units and what your pixel size is. And then if you run this cell, you get like a printed summary of your emitter set. That's 2 emitters in XY unit pixel, and the pixel size is this and that. You can also like implicit or automatically convert the units. So if you now call em.xyz_nanometer, then it will automatically convert to nanometers for you. Okay, and now if you here want to set something in nanometers, for example, random number, this is like a random number of size 2 times 3, then you see that decode converts your emitter set into nanometers, and you see how big it is, basically. Good. Yeah, so as I said, this is just really basic information on how to use decode. If you want to export something as a CSV, we have this export functionality. So it's decode utils emitter input output, save CSV, you give it the file name, and then say em to dictionary. Then if we run the cell, we can see how the CSV file looks, right? So this is like literally what is written into this dummy CSV file. So it's just the coordinates and all the other information if present. Okay. Yeah, if you want to have fast in and output, you can also save in a PyTorch native format. This is just if you want to like have one Jupyter notebook of decode and want to transfer your emitter set from one notebook to another one, then you can just call em.save directly. And then you can open and load this via decode.emitterset.load. Okay. So I'm not really sure how familiar you are with Python, but you can do a lot of things with these emitter set. For example, you can extract, or you can use Boolean indices. So you can say, I want to have the first one, but not the second emitter. Or you can select emitters by saying, I just want to have the emitters where the frame index is 0, or I want the emitters where the photon counts is bigger than 600, for example. And yeah, and then if you, for example, say print em sub, so this is just the emitters which are on the first frame, right? So you have the emitters, then the bracket, and then say they should be on the 0th frame. And you can double check then by printing it, and you see that they are in fact on the 0 frame. yeah, and you can also check that two emitter sets are equal by just using the equal sign. Okay. So this is maybe not so interesting from an academic perspective, but it's really useful if you're working with DECODE to know these things. And then what is also interesting, if you want to split emitters into the frames, you can do this. There's this function em.split in frames, and then you provide a lower index and an upper index. And then you basically get a list of emitter sets. You see, right, if you print now what you have here, then you see that you have a list where each item of this list is one emitter set. And then if you check, for example, the third one, that there was in fact no emitter set, but since you say you want to go from the 0th frame to the 10th frame, you can have some of them where there's actually no emitter on this frame. And you can also concatenate them back with the cut function. So you say decode emitter set dot cut and then concatenate them back. Good. Then sometimes it's interesting to sample some emitters at random. You also have some convenience ways to do this. So you just say decode.random emitter set and the number of emitters you want to have. And in fact, you see that you now have two emitters placed at random positions. By default, it's in a 32 times 32 window. Okay, and then lastly, we have basic plotting functionality. So for example, here we again sample 200 emitters at random. And then we have this plotting function, which just reads decode.plot and then plot coordinates or plot coordinates 3D. And then you need to provide this with the appropriate unit. So if you want to display it in pixel units, then you say XYZ underscore pixel, or you could also say underscore nanometer, however you want. And then if you execute this cell, you see your emitters in the 2D projection and also in the 3D projection. In the break, we ask you to download the beat calibration, and now what we want to do is to fit the beat calibration to this. So if you go to the location where you have stored your beats, then you see that you have like a couple of folders where the TIFF files of the beat stacks are. And I would like now, I would like you to open SMAP now. So if you have the compiled version without the need for MATLAB, you should find in the applications folder. And then you can just open SMAP by double clicking on this. Then it takes a while, but then should show you this here on the this SMAP GUI. Maybe I'll wait a couple of seconds until everyone has done this. Okay, so if there are no objections, I would continue now. Yeah. So, and then in SMAP, you go to plugins. Oops. And then analyze. And then there's under SR3D, there is the plugin calibrate 3D spline PSF. And then if you click on this, it will opening up like a helper window, and you can just click on run. And then this is the interesting figure actually. And now the first thing you would have to do is you would have to select where the beat calibrator, like where the beat stacks are, the TIFF files. And for this, you just click on select camera files. Yeah. And then you say add directionaries. And then you navigate to to your file. Okay, this is now a bit more users. Yes, yes. And for me, it's desktop. Yes. Decode workshop, and then you go into the folder and select all of those directories. Then you say choose, and they should be then here in the file list. So it now loads. It shows you the preview of the TIFF files there directly. And then you say done. And then you can find them here in the file list. And that's basically already all of it. So you can say how big you want your calibration to be, but 27 is quite big and already a good start. So you would now can just say calculate beat calibration. Of course, if the frames have a different set step in the axial direction, like a different value rather than 10, then you need, of course, to specify what was your axial step. But for now, for this file, this is fine. So then it takes a while. You can see the progress.
Maybe while we're waiting, I briefly can tell you what this program does. So basically, it finds beats in each of the stacks, and you see it as these circles here on all the files. Then it cuts out regions around the beat a bit larger than your ROI size. Then it uses 3D cross correlation to shift the beats on top of each other, or to find the relative displacement between the beats in order to shift them on top of each other in the end with subpixel accuracy, and then it just averages the beats. And finally, we perform a B-spline smoothing, spline smoothing in the direction of Z, and the direction. The reason is that because of fluctuating laser powers, because of blinking of the beats, sometimes the profile in Z is not totally smooth, but a little bit wriggly. And this is not good for the fitter. And we use usually these functions for normal fitting because then the fitter can get stuck and not go to the next Z position. And you see it here sometimes for the individual beats. For DECODE, it might not make a difference if you do the smoothing or not. But because we average so many beats, we get actually quite smooth representation, a quite accurate representation of the beat. So you see here, that's in the Z direction. Maybe we can check it out in the X direction. And of course, we have only a few pixels. And you can also explore how the beat stack, the average beat stack looks like. The advantage of looking at many beats together is that you increase the signal to noise ratio, and also that you, to a certain extent, average over feed-dependent aberrations. Yeah. So maybe something which is nice to check always is this validate. Yeah, maybe Lucas, you can click there to just see that the fitted Z position are linear with a frame over a certain range.
Yeah. Okay. Good. Yeah. So just when this is done, you should find in your folder, which you selected, you should find the figure, which is just a validation figure here, and you also find your actual beat stack. Right, so make sure that you somehow know where this is, and then lastly, I would now show you how you can load this into SMAP, into DECODE. Sorry. So I need to copy this now. Give me 1 second. No. Put it on the desktop, wherever. Takes a couple of seconds. And now we go back to the DECODE notebook. And the last thing I would like to show you as a general introduction would now be how to load this calibration into DECODE, because you might want to use it for other purposes of simulation or something, which you can actually do. So let me just say load PSF calibration. And for this, you can call the utilities function. So you say decode.utilities, and you can always, if you're not familiar with Jupyter, you can click on tab to get help or auto completion. So now you would say decode.utils, and then you already see it here. It's calibration input output, and then you see here that we have a default interface for this map spline coefficients, right? And then maybe one can add the path here, so the calib file, and then you just provide the path to the calib file. And it should be somewhere there. Give me 1 second. Oh no, it's actually a different one. Yeah. Okay, and then you see that it already has auto completion. Then you can say, can also call the help with shift and tab. And you see a short description, and you see that here you need to provide the path to your calibration file. So we just say calib file and can put it there. With this, you don't have the PSF yet because you need to specify how big the PSF should be and how great the extent and X and Y should be. So what you then need to do is you can say PSF loader.init spline. Yeah, and if you click then on tab, you see the kind of arguments you can give to this function. And in this case, you would specify the X extent, the Y extent, the image shape, and whether you want to run this on CUDA or via CPU. So now you would say X extent and a pixel center. The pixel center for us is always the 0 in DECODE. So you go from minus not 0.5 to 31.5, which is then a size of 32 pixels, and the same in Y direction. And then you can also need to specify the image shape, and then you say if you want to run this on CUDA or on the CPU, and that depends, of course, on your machine. So if you have a CUDA capable device, you say CUDA kernel true, and now you have a PSF. Okay, and for example, what you can do now is could just simulate all of these emitters, and for this you would just say PSF.forward, and now you can again open up the help, and you now just need to specify the coordinates and the brightness of them. So if you take the ones from here, for example, you can just copy this, EM fuzzy, XYZ in pixel coordinates, and the weight is just the photon count. And what you get out of this is the frames. Oops. What have I done? Oh, maybe I have. No.
You have once EM fuzzy and once EM.
Thank you. Yeah, and now you get the frames, and you can, so if you now have a look how big the frames are, frames.size, you see that it's just one because all of them were on the same frame. And now you can, for example, use the plotting in Python and get your simulation. The more sophisticated way is via this function, which I just copied from here. And then you can say decode.plot and then plot frame coordinates, because there you can overlay emitters and the frame, right? So what I can do now is say, I want to have the first frame. Oops. And here you see now the overlay of the emitters on the frame. Yeah, and in the CUDA, with the CUDA kernel, it's quite fast. You can simulate like 200,000 PSFs in under a second or so. Yeah, Good. Questions until here? Then I would hand over to Artur.
All right, so now we will go through the same two steps which we already dealt with in the Colab notebooks, but now we do it here with our local installation. And I'm using the classical Jupyter notebook instead of Lab, but it's very much the same. I just have them here as different browser windows. I just never got used to Jupyter Lab. And I have some features here that I don't want to give up. But otherwise, everything is the same. And there will be, of course, some repetition here because the basic steps are the same. But we will go into a bit more detail. And again, this is how we kind of want you to use the program once you decided you do want to use it, maybe regularly. So again, try it out, maybe upload some data to Colab and try it out there, see if you like it, if you get some promising results. But in the end, this is the more convenient and also faster way to use the software. Okay, so again, we start out with the training notebook and we can just execute again the import. And then we set our parameters, and we do it in a slightly different way than than previously. So we start with some hardware parameters, and the first important one is here setting the device. So again, if you have a GPU available, you can you should keep CUDA chosen here. Otherwise, you can change it to CPU, and it should run, but it will be maybe 10, maybe more times slower. And if you have multiple GPUs available, maybe you work on a cluster or something, then you can choose the GPU here with the device. And then the other things you normally shouldn't touch. Now again, in this case, I will use the same data as in the Colab notebooks, which I downloaded before. So if you execute that cell, it will download about 1 gigabyte, including the frames, a trained model, and the spline calibration. You can also use the spline calibration that you just did. And here in the next text cell, there's a little bit of information about what Lucas just talked about. So again, if you want to use your own calibration file, you can just uncomment this comment and put in the path to your calibration file. All right. And then we go to the simulation parameters again. Now, the way you would normally do this is you start with a reference file where all the parameters are set to default values that are reasonable and that work. And then you change all the parameters that you need to change. And this is what we do here. So we copy the reference parameter file into our current working directory, and it's called param-friendly. And then we start changing the parameters that we want to change. And in this first cell, we just take over that parameters that we set up there. So here we we just give the hardware specifications. So which device do we want to use? And then how many CPU workers we want to use for data loading and so on. Now the really interesting part then starts below. This is where you set the camera parameters. And these are basically the parameters you will have to adjust in any case. And you will get the specifications, hopefully, from the manufacturer of your camera, or if you build your own camera, well, you'll just have to know these parameters from somewhere. And again, one thing you can do is if you use SCMOS instead of an EMCD camera, you can just set EM gain to none, and you will just work with the remaining parameters, and that should work. And again, stuff like variable noise maps are not implemented yet. Okay. So in this case, these are the parameters of our camera. And next up are the simulation parameters. Now, the simulation parameters, there are two ways to set those. One, again, is using SMAP. And here's a short description how you would do that. And what happens then in SMAP is it just fits a couple of frames and then estimates the simulation parameters from those frames. And this is kind of the safe way to do that. But what I did throughout development was also basically, well, eyeballing it. And that also works, and it's fairly easy. And this is why I'm going to show you how to do that. And again, the goal is to generate data that looks as close as possible to the real data. So this is why this time we will also load some frames, or all the frames, so we can compare our simulations to those frames, and then adjust the parameters accordingly. And these are our simulation parameters. We have the background, and we will now just go ahead a couple cells down and actually load the frames. This is this cell here. No, wait, where is it? Data frames. No, it's one cell below. And we can take a look at them the same way we did before. So we do PLT show data frames dot mean 0. And what you can see here is that basically, or that the background is not homogeneous over your whole frame. So here, there's not really any signal, but still there's a higher background than here in the corner. And this is what we try to capture with this range. We can also plot a color bar to get an idea of. So here the background is maybe around 30 in that corner, and then here it's probably around 70 or so. So this range is, well, it's rather large. We can probably reduce it to 100. And you might wonder if how we simulate the background. And what we actually do is we just simulate a random uniform background in each of our 40 × 40 frames. And we also tried out non-uniform backgrounds. But actually found out that uniform backgrounds do a fine job, actually. So we don't need the more sophisticated non-uniform backgrounds. Just using different values of uniform backgrounds, that's the trick. Then the next parameter is, again, our emitter average, which you should adjust according to the density of your data. Then we have here the emitter extent. And this is now in Z direction, which is the third dimension. So 0 is X, 1 is Y, and 2 is Z. And then we have the intensity in mu and sigma. So this is the mean number of photons that each emitter produces, and then the sigma of that value. And again, the sigma, it's not too important to set exactly the right value. Something like a third or of your mean value will do the trick. And the intensity should be chosen such that it kind of covers the whole range of intensities you see in your data. And it's always okay to go a bit higher. You don't want to get lower because you don't want that your network sees stuff that it has never seen before at test time. But if you go a bit higher, that's mostly fine. So always, just give it a little bit more wiggle room. And then the lifetime average, this will be a number between 1 and 2 mostly. It kind of depends on your camera setup. Yeah, just a value around this, you can never go wrong with that. Okay, so if we now execute the next couple of cells, again, we set up our simulator. And what we do here is then we sample a couple of frames, and we also load our data frames, which I already did before to show them to you. And so what we have now is a simulation of 10,000 frames, and we have our 20,000 real images. And if we just look at the mean values here, so I just print out the mean of the simulated frames and the data frames, we see that there's a large discrepancy. And the reason is that we decided that we always work in the photon space, basically. So what we sample are photon numbers. So this means these are the actual photon numbers, and then to actually get the frames, we have to apply the camera with the EM gain. And so what you can do is you can transfer your data frames basically into that photon regime by using the camera backward function. So this just means that the data frames get downscaled so that we can estimate the actual number of photons that were recorded. And if we do that and then again compare the mean values, so before it was 207 to 1600, and now I made some mistake because I downscaled them twice probably. So I'll just reload them and hope. What did I do wrong?
What was the number? Sorry, I didn't.
Oh, no, I set EM gain to none before, so that was my mistake. It should be 50, I think. Something like this always has to happen, so I'm just going to execute everything again.
EM gain should be 100.
100?
The training notebook, it should be 100, I think.
All right. Okay, so now we are kind of closer to what we expect. So the mean value of the simulations is 107 and of the real data is 60. So it's still a bit higher, but this is probably expected because we also have a very high density. And what I do in the next cell is I just compare a simulated frame and a real data frame, just a random one from a certain region. So I cut a 40 times 40 region out of my real data and compare it to simulation. And I can just do that a couple of times and this way get a feel of, do these somehow look similar? And we see that kind of the background distributions are somewhat okay. Of course, it kind of depends on, again, we sample backgrounds between 20 and 100, so you will get different values. But overall, these look fairly comparable. You can see that mostly the range on the left side is higher, so you might want to tune down the intensity maybe a little bit. Let's do 5,000, 2,000, run all of these again. And again, this isn't really, this doesn't have to be 100% exact. So here you get a pretty nice match already. And if you're unsure, you can also use the SMAP software to set these parameters. But here, again, so these look, it would be hard to distinguish between the real data and the simulations. So once you're happy with your parameters, you can save them to an output parameter file. In this case, I called it notebook example, and I'm just going to store it locally. And then we are ready to start our training because again, we have our parameter settings and we have our point spread function, and these are the two main ingredients. So how do we start training? Actually, I have to now share my screen instead of just this window. Okay. So now you should see my whole screen. So I just go into the terminal. And this is where I stored my notebooks. So we now have here my notebooks and we have the notebook example file, which you also should have, I hope. And then you can execute this command. So you can just copy this paste it in. And this command basically executes all the steps that we did previously in the Collab notebook at once, just using one parameter file. So it sets up your simulator, it sets up your model, and it gets the training going. Out of memory. Okay, I probably opened up too much stuff. Yeah. So I guess I have something open somewhere else. Oh, yeah. Actually, there's someone else also working on this workstation, so that's a little bit unlucky. But this is actually a useful thing to show you. So if this happens to you, or maybe you want to train multiple models at the same time, one thing you can always do is reduce the batch size, because the batch size determines how many frames you process in parallel. And if you run out of memory, it's always reasonable to just reduce the batch size to use less memory. So we can check our parameter file. And then, okay, so this is not the nice printout from before, but I think it's param, hyperparameters, and then batch size. Yes. And right now it's 64. So let's just reduce it to 16 to be sure. And actually, the easier way to do this is we don't actually need our notebook here. So you can just go to your folder, open up the notebook example parameter file, and there you have it nicely. And if you want to just change one or two parameters and you don't want to rerun the simulations to check how they look, you can just change it here and then re-execute the command I showed you. So let's look where our batch size is. It's right here. We changed that, we save it. And then I can't guarantee that it will work. But maybe if I just close some other stuff. But for you, it should work. So now, obviously, it's a good point to ask again if who got through all these steps successfully and got the training running and who has problems. Okay, so now it seems to work for me. So yeah, if you run into memory problems, just reducing the batch size is the easiest.
So could everyone follow and reproduce?
Again, you can give us a thumbs up.
What you could also do is maybe start the TensorBoard. After.
Exactly.
Oh.
So that's the other thing we do here is run the TensorBoard. And I'm just going to quickly change into oh yeah, I already am running TensorBoard. But if you just execute that command, which I just copied from here, then you should be able to find your TensorBoard under this address, which you can also just click here. And it looks the same as it did before in Colab, if it runs. Which right now for me, yeah, there it is. Well, I was there for a second. Okay, I'll just continue and wrap up the fitting part. And then again, if anyone has more problems, we will work on that maybe separately, maybe together. All right, so the second part, again, is similar to what I did previously in the colored notebook. And it's about using the model that we just trained to fit the data set. Now the first cells basically have exactly the same commands. So you set your hardware parameters. And then we choose our model. So down here, you have again the possibility to download the package and use the pre-trained model. But right now, we're not going to do that. Instead, we're going to use the model that we just trained, and we can check where it is. So for me, it's in this folder. And this will have a different name on your workstation. So you just have to check which folders were created, and it will have the today's date and then probably the name of your workstation. And if you click on it, then again, you have these files which get updated continuously while the model is training. So let's put this in here. And then you give it the parameter path and the frame path. Now we also have this meta directory. And the idea behind this is that you might want to use different camera parameters at test time than at training time. Now this won't be often the case, but we kind of wanted to keep open the possibility. So maybe you use the same point split function, but just change the EM gain, and then you don't have to retrain the whole notebook. You can just change it here. But mostly you don't have to change anything here. So I used an EM gain from 100, so I have to use this here too. And then we can basically just execute the next couple of cells. Again, here we load our model, we load our parameter, our camera, and we convert. No, here we load our frames. Yes. And then again, what I do is I cut out a little piece from the frames. So this box on the bottom left, so that I don't have to run the network on the whole, on all the frames, which would take a bit, but you can do that, of course. And here we set up the pre and post processing. So this is basically, this scales the images before we feed them to the network, and then that sets the post processing. But most of the time, you won't have to change anything here. And then again, we fit the data. And okay, I have enough memory over. Normally, you can run out of memory if you train a network and then at the same time try to fit the data. Okay, now this model only has trained for a couple of maybe 2 or 3 epochs. So I'm not sure what we'll get out here. It will probably look a bit messy. But it might still be instructive. Okay, so here again we see, well, actually on the left we see the input frame, and on the right we see what our network does. So it did definitely already start to make reasonable localizations. But if we actually render it, there might be some artifacts. Right. So here you can now see some of the artifacts that I previously described. Now on the edges, these are just artifacts because you don't do the full convolutions at the edges, and you can ignore that. Normally you would cut that away, so you don't have to really bother with these things. But then you see some slight artifacts also in this reconstruction, though they are not very, very prominent. So here you see these kind of stripes. And again, these will disappear after a couple more epochs. But if you see some of those in your final images after your model has converged, then what you would do is in post-processing filter out some of the localization with the highest uncertainty, and then these should disappear. And down here we have basically the same procedure as in the Collab notebook, where we set the thresholds for X, Y, and Z, and then just remove them. And you see if I set the thresholds like that, then I remove 24% of the emitters that I inferred. So I'm left with 76%. And then we have some less artifacts. There's also a second way to filter out. Let's say you want to remove 60% of the worst emitters. Then we have this function down here, which is called filter by sigma. And here you only provide one number, and this one number tells you what's the share of emitters you want to keep. So in this case, we want to keep 40% of the emitters and throw away all the rest. And then it kind of combines the X, Y, and Z uncertainty and weights them by their variance, and this way ranks all the emitters by their quality and then throws away as many as you want. So in this case, we're only left with 40% of the emitters, and now we don't see any artifacts anymore. And it even removed all the localizations at the borders because, well, there's high uncertainty associated to these. So again, this is what you can see is that while training can take up to 10 hours, even after a couple of minutes, you will already get a reasonable output, and you can check if you set your parameters in a decent range so that the training works. And then again, the last step would be to save the emitter set. And yeah. So I will quickly go through one last thing before we open up for questions again. And this is basically, I just want to mention that there's one more notebook, which is called Evaluation. And what is described here is how you can evaluate the performance of DECODE if you have ground truth data, if you have ground truth information available. Now, this is obviously not very interesting if you're just, you're a practitioner who wants to use DECODE for real data, but maybe you want to try out some change on the algorithm, or you want to compare it against another algorithm that you think about using, then this might be useful. So this shows you how you can, use two emitter sets, one ground truth emitter sets, and then the predictions from DECODE, and then you can match them and compare them, and it will give you all these performance metrics that we talked about when I was talking about the tensor board. So this might be useful if you want to develop or compare or something else. But right now it's probably not interesting. Also, my tensor board started working, and again, actually, I have some training runs from before. So here you can see how you can compare different training runs if you have them. You can just choose them here on the left side, and then it will plot them over each other. And okay, I think that's all from me for now. And now would be the time to ask all your questions. If something went wrong, we will try to fix it. And also maybe as one last thing, of course, we hope you got something out of this. And what would really help us is if in the next time you maybe try this out on your data, if you think this might be something which might help you with your research. And then we are really, we would be really thankful about any feedback you have. Like if it works, if it doesn't work, then we will try to help you. Also, if you get good results, obviously we're happy to hear that. If you get bad results, that would be also very interesting for us. And just in general, I would say that there are cases where performance probably won't improve with DECODE. Like if you have data which is clearly in the single molecule regime and you have another algorithm that is well tuned, then it might be that that's the best performance that you can get. And then DECODE will probably perform the same. But if DECODE really performs worse, then it might be an indication that something went wrong in the fitting process, because in our experience, it at least does as well as the other algorithms. And if the circumstances are more difficult, then DECODE really starts to shine. Yeah, so that's it from me. I guess at this point, it would be again nice to get a round of feedback about if this, who got it to run, who got the training running. And well, we know already about a couple of cases where there were problems with getting the installation to run at all.
I added the TensorBoard is one question. So you basically need to open up a new terminal window and then copy this command, which is at the bottom of the training notebook in this new terminal window. And then you can open your browser and watch the TensorBoard from there, basically.
I think at this point, if you have any problems, you should let us know. But how many got everything to run properly? What fraction of everyone? Show of hands or emojis, reactions? Okay, so one, and then, oh great, three people, 4, some crying, tears we can try to help with. Now, you know, one thing we can do in the remaining sort of 15 minutes that we have is, I mean, of course we can continue as well. If you can tell us what problems you're having, we could try to group you by problems. And then help you sort of in little breakout rooms. Does that sound good? Or are there any other comments, questions that maybe we should take as a as the whole group?
Yeah, also there's a second tutorial tomorrow. So if you want to tell us what we should do better tomorrow, now is also the time.
I have a question. How do you deal with frame skips in your data? Like if you have an activation frame for Palm, how do you incorporate that time skip into the training or the fitting?
Can you repeat your question?
How do you deal with frame skips in the data? So if you have a, let's say, if not all of your frames have single molecules in them, some frames are, let's say, used for activation or maybe an LED frame. How do you incorporate those? Because you're now using time information also. So you'll need to account for that frame skip.
I see. Yeah, so we don't actually use the precise time at which a frame was acquired. So you're welcome to break up your entire acquisition into blocks and then run the fitter on those blocks separately. So that's no problem. It's just that if you're leaving out frames in the middle, it's better to split them up into blocks so that the temporal context doesn't get confused and think that the last frame of the first block and the first frame of the second block are next to each other. So just sort of break them up. But other than that, there's nothing really that it cares about too much. It only cares
also
about
also if this is like 2 out of 10,000 frames, you can probably ignore it, right? Yes, probably, you know.
Yeah, and in the sampling, you will also just stochastically will have emitters which are on for less than a frame, right? So this is nothing new to the network in that sense.
Thanks.
Anyone else? Any comments, feedback? Memory errors.
Okay. So out of memory or CUDA out of memory error? Or probably.
It is suggesting me to buy a new CPU.
Yeah,
that's reasonable.
Yeah, that's actually from PyTorch.
Because I was having problems, like I've been having problems for a while. Then I restarted the kernel, and now it worked. It went through, but I'm getting a new memory error on the step.
Okay, so maybe for this, you sometimes need to check that you don't have 10 notebooks open at the same time and all of them plugged in.
Yeah, I was trying to do some stuff, and also I reduced the batch size.
Yeah, so what you can do is you can just click here and then kill all of them. And then sometimes that is it already.
Okay. Thanks.
And the other thing that can sometimes happen, which I guess happened to Artur, is that other people could be using the same computer at the same time, and then you might run out of memory. Now, just to be clear, that error message is more tongue-in-cheek than it's intended to be, I think, from PyTorch, about asking you to buy a new GPU. I think if we want to think about how much memory you need, basically all of the modern GPUs should work. We've set it up, the batch sizes and so on, so that all the modern GPUs should work. It's just if you are in the really fun situation of sharing a GPU with multiple people, or you're running multiple jobs at the same time on the same GPU, which you can do. The code will let you do it very happily. Then I think that's where you can try to play with the batch size and make things run. So if you have a GPU, I wouldn't run out and buy a new GPU just by looking at that error message. I would suspect that probably there's something else.
Yeah, and also if you have like 5 4K monitors connected to your GPU,
now
that
it seems to work.
might also be an issue.
I closed other stuff that I was running. Now it seems not to complain, at least.
And I don't know, Lucas, do you know SMAP, how its use of the, does it use the GPU for the spline fitting? It does, right?
Yes, if you really fit your data and not only do the calibration, then it uses the GPU.
And then does it give it up after, or do you have to close it explicitly?
No, I think I don't know how much memory it actually uses, Jonas, if you know this, but I think it's more utilization.
But during the fitting, well, it has to store the spline PSF in the GPU memory, and that's kind of the limiting factor.
Yeah.
But then it should give it up in the end.
Great. Yeah, so if you have SMAP still open after you finish calibration, it shouldn't hurt you, I guess.
But who knows? Could close it and try it.
Yeah. So yes, those of you who perhaps were, got sort of delayed at some step and need to catch up and weren't able to catch up, certainly we will have the recordings available, but because we have another session coming up tomorrow, if time zone wise it works out for you, please join us. I will post the Zoom link for tomorrow's session in Slack, and come join us. And if you're still having trouble, then maybe we can help you out.
And then more generally, you can always write me, you can write Lucas about any problems you encounter. If it doesn't run, again, if the results don't look as good as expected, because we think they should. And the other thing you can do is open up a GitHub issue that's something you're familiar with. So any of those are fine.
Yeah, this is really new software. We've really just developed this. You can help us improve it in many ways.